Hello to everyone. Thank you to be there to this third event on the PRELUDE Project Educational Lecturing Series, so educational event series. Today we will have this very interesting series of two presentations by Professor Agnese Salvati and Professor Massimo Palme. We'll go a bit in detail on it in a second. That was very kind and comes to present us part of their work on urban climate, urban and urban physics, and microclimatic connected issues. Today we will have in this lecture a very short presentation of the background of this educational event series. So it's done of what? It's done by a series of lectures. I think that part of the people here in present already followed one of the previous ones. That's organized in between 2023, since January 2023 till the end, near the end of 2024. All lecturing are organized in a hybrid mode, including in-present people and remote connected one. It is devoted to students, university mainly, to professional, to researchers in general, and people interested in following a specific topic on the link. Speakers are all recognized and internationally recognized and expert. We have seen speakers from the industry domains, from company domains. We have scholars, mainly of teacher, comes from the university sector or research sector. We have already two lecture series. First one on proactive forecasting on optimization of project for intelligent building, mainly devoted to an ICT expert audience. We had a second presentation on free-running zero-energy building and climate-correlated solution devoted to designer and engineering and architects working in sustainable design topics. And now today we will arrive to our third event, which is about urban climate dimension, urbanization and microclimatic issues. Again, the target may be architecture, engineers, and researchers working in the sustainable design domain, energy efficiency building, and you can say building physics, urban physics. The next event is expected at the beginning of the next academic year, so something like in between beginning of October and November. We will be a series of 2-3 events focused again on ICT and ET and EOT experts, followed again in the next spring on climate comfort and bioclimatic solutions. If we look a bit inside, this educational event series is part of a PRELUDE project, which is Precision Building Operation utilizing real-time data for energy dynamic optimizations, which is funded by the European Union Commission under Grant Agreement 958345. And I'm to support low energy, low-cost solutions with innovative and smart building for proactive optimization services, minimizing energy use, maximizing the sense consumption of renewable sources where present, and improve internal comfort condition, different type of comfort, maximizing the exploiting the free-running potential of this building. Inside the project is developed a modular platform with a different series of tools and solutions connected to a shared middleware. For example, among proposed technologies, we can remind the integration of all data connected to the project, both simulation, monitoring, and elaboration inside a sole middleware. The dynamic free-running potential exploitation with a new Energy Plus and monitoring data interface, which is called PREDICE, developed at POLITO. The outdoor-outdoor correlation model, supported by the Bull University. A prediction model for weather, irradiation, and building energy forecasted requirement, developed by companies inside the project. Occupancy profiling and advanced profiling methodology using different type of machine learning, provided by the FB Research Lab in Austria. District heating integration model supporting the integration of building in between smart grids. And you can say green and energy communities, renovation roadmaps through simplified and advanced tool for architects, comfort and energy efficiency optimized, connected together, monitoring, optimization and control of equipment in the buildings, predictive maintenance, measurement and verification approaches with machine learning, and so on. These modules are under test now in different demo cases, from Denmark to Italy, from Switzerland to Poland, Greece, and including a very advanced smart building living lab, which is in Austria. But if we go to the event of today, which is part of this educational conference series, the event of today focus on what? Open to this discussion on the free running and low energy building, the topic of the urban dimension. We always know that urban dimension is changing a bit we can say the domain, at least we can say the boundary condition in which we apply bioclimatic, low energy technology and solution. The topic of today is to introduce these problems, see some advanced research on the topic, including urban Island issue, including urban physics theory in some way, green infrastructure and other countermeasure to the urban Island, and all the aspects connected to urban microclimate and connection with buildings and people comfort. The two speakers that we have today, I'm very happy and I really thank you both of them to be there today, are Professor Agnese Salvati by the UPC Spain University and Professor Massimo Palme by the USM University in Chile. In particular, Agnese Salvati works now at the Universitat Politècnica de Catalunya in Spain, and where he acts as lecturer, so it's an associate professor level on urban microclimate and the climate impact of building thermal performance. That's the title of the presentation. I've stolen a bit a description of her in ResearchGate, but we know each other since several years, so I fully know that she is one of the major experts, at least working now, emerging expert in the urban domains and urban climate issue in Mediterranean climate, at least for Europe, that's totally true, with supporting also the connection in between urban morphology and building energy performance and urban climate. The second speaker of today is Professor Massimo Palme from the Universitat Tecnica Federico Santa Maria of Valparaíso in Chile, which is, again, a great expert and recognized expert working on the urban Island topic domain and in low energy and sustainable construction domain with climate change adaptation and urban climate studies. And today he will, again, speak and work on urban Island mitigation in supporting Mediterranean climate. You know, also in Chile there is a Mediterranean climate, part of the coast is Mediterranean. And that's totally interesting for all the Mediterranean climate that we will have, like the one where we live in Italy. That's a bit. Clearly, Massimo has a lot of experience, like Agnese also have, and is also a present president of IPSA in Chile, and has a lot of other connection with international recognized institutions. To conclude my short presentation and leave the floor to Professor Salvati, which is clearly the most interesting part of the speech of today, the two lectures done by Agnese and by Massimo. I only need to remind that the educational event series of the Project Prelude is inside a large task that we coordinate as POLITO, in which we work not only on the educational activity, but also on citizen science, directly involved in students, directly involved in students at different levels, from the high school to the university or post-university, and including also works connected to the fact that we are developing and we are supporting population and especially young child in school involvement in smart buildings. For example, in parallel to that, we organize didactical activities that include, for example, the development by students to students of multi-comfort monitoring kits, clearly supporting an Internet of Things domains and microservices. We have developed a different level of comfort monitoring kit for schools. Next year, if everything will work well, we will have, for example, the fact that the work done by students at university right now will be passed to high school students to a production, okay, of low-cost multi-comfort kits with high quality of results that will be, after potentially at least adopted, but for sure tested, under the support of the Piedmont regions in several schools. In addition to that, we also have the development of low-cost meteorological station to support real-time feeding of digital twins and simulation and this type of action. And so please, Agnese, take the presenting role and let us.
Thank you. Thank you very much, Giacomo, for the very nice introduction and for inviting me to this event. Today, as introduced by Giacomo, I'm going to present some studies related to the impact of urban climate, urban microclimate on the building thermal performance. But more specifically, I will add also another effect that has an influence on building thermal performance. So we will see a couple of researches that investigated the combined effect of urban microclimate and climate change on the thermal performance of buildings, which I think it's interesting also for the PRELUDE project. So a brief introduction to this kind of climate phenomenon. When we talk about urban microclimate, I think you can be familiar with the phenomenon of the heat island effect, probably. I don't know. So the heat island effect is a local climate phenomenon that determined higher air temperatures in cities, in the built environment, especially at night. So cities are generally warmer than their surrounding rural environment. So an increase in air temperature, of course, has an impact on the heating and cooling demand of buildings. But in cities, there are also other microclimate modifications that have an impact on the performance of the buildings. And in particular, we have a reduced wind velocity in between buildings due to the complex geometry of the urban surface and the proximity of the buildings. Which, of course, decreases the ventilation potential of buildings. And another effect is the fact that we have reduced sky view factors of the roads, of the facades, that basically slow down the cooling process during nighttime for long wave radiation loss. So we have a modification of air temperature, wind speed, and surface temperatures in cities. This effect determine an overall increase of the energy demand of buildings, because in the literature we can say that it's quite common to all the studies that even if we have a saving in the heating demand, the increase of the cooling demand determined by this urban effect is more relevant. So overall, buildings in dense urban context have a higher energy demand than outside the city. And generally, we can say that the increase of the cooling demand is around the 20% of the same building outside the city. But of course, this depends a lot on the climate, on the building, on the texture. So this is just an average result of the literature. Then every case is different. So we have these urban effects that determine an increase of energy demand of buildings in different climates. And on top of this, we have climate change. We know that the climate is changing, and it is changing toward higher average air temperatures. So we have, on average, higher temperatures that also have an impact on the energy consumption of buildings, especially the cooling demand. And we also have more frequent extreme events like heat waves that have impact on buildings, but of course are even more concerning for health-related risks for the population. But if we think that we have this average increase in air temperature combined to the heat island effect and the other urban microclimate effect, it is clear that urban microclimate is actually amplifying the negative effect of climate change in cities. So when we analyze the performance of buildings under climate change scenarios, we also must be aware that on top of that, we also have the climate effects. And this is what we have tried to analyze in a previous European project, the RECOS project, in which I worked when I was postdoc at Brunel University. So the studies that I'm going to present are basically results and methodology developed for the RECOS project, and specifically for one task that was devoted to assess the resilience of renovation solution for buildings, the resilience of these to the impact of climate change and urban environments. So these are research activities carried out at Brunel University with Maria Colocotroni, which was the PI of the RECOS project, and which is also involved in the PRELUDE project. So it's a good thing for the PRELUDE to have this expertise inside. In the RECOS project, there were different demo buildings, of course, and we focused on two of them, one located in London and one located in Cadiz in Spain, to analyze this combined effect of microclimate and climate change, because they were like representative of very different conditions in terms of climate region. Of course, in London we have a humid, temperate climate, while in Cadiz we have a hotter Mediterranean climate. The two buildings were similar in terms of, let's say, performance of the fabric, which was quite poor, and internal gains. There were two, a student hall in London and a social housing in Cadiz. But they were located in a quite different urban context, as you can see in the central images. So in Cadiz, the building was located in very dense urban fabric of the city, while in London it was located in the campus of the university in a much more open context and greener context. So it was interesting to analyze how these different boundary conditions affected the performance of renovation technologies applied to these buildings. Okay, so the first thing that we did to analyze this combined effect was to develop a methodology to include the urban heat island intensity in future weather files. So in order to run simulation using future weather files that were also including urban effects. And to do so, we used the urban weather generator tool, which is an urban canopy model that has been developed exactly to include this heat island effect into weather file to run building performance simulation. And we forced this urban weather generator using future weather file data. In this case, generated by Meteonorm. So we generated a future weather file from Meteonorm, and we use this to force urban weather generator, obtaining a future urban weather file. And in this graph, we can see some results of the change in mean air temperature determined by climate change and heat island effect in these two cities and different contexts. So the yellow part of the bar represents the increase of temperature determined by climate change, and the red part, the further increase determined by the heat island effect. And you can see that, for instance, in Cadiz, the graph on the bottom, the heat island effect is as high as the increase of air temperature determined by climate change. So it is very important to consider both effects. While in London, in that specific location, the heat island effect was lower and the impact of climate change was more significant on mean air temperatures. As a result, if we analyze how this increase in temperature affect the cooling and heating demand of these two buildings, if you see on the graphs on the right side, for instance, you can see that a comparison of the cooling and heating demand using a contemporary weather file, a future weather file, and a future weather file, including the heat island effect. And it is clear that the cooling demand is increasing more than the decrease of the heating demand. So overall, we expect a significant increase in the annual energy demand in both climates, in both London up to the 16% and Cadiz up to the 28%. And the results are similar if we analyze free-running buildings. So instead of analyzing energy demand, we just analyze free-running building and see what happens to the indoor operative temperature under these future urban scenarios. We can see that in London and Cadiz, these results are for different rooms of the buildings analyzed. We can see that there is an increase of the percentage of time that the building is above the adaptive temperatures, even considering the upper limit of the adaptive temperatures. So in both cases, the climate change plus heat island effect will determine some very discomfortable condition, like that 75% of the time the buildings are above like 28.7 degrees in London or above 30.8 degrees in Cadiz. So this is really, and in Cadiz, for instance, the increase determined by heat island effect is even higher than the increase in discomfort determined by climate change. So this is again to underline that it's really important to consider both effects. And finally, there are also other microclimate effects that cannot be included in weather files. So in weather files, we can assess, we can modify the air temperature according to the heat island effect and run simulation to take into account this effect. But we cannot take into account the impact of the actual spatial distribution of wind speed and direction around the building and the surface temperature, for instance. So in order to assess what was the further impact of this microclimate phenomena, so phenomena that are happening at a very small scale around the building, we used MVMET. MVMET is a CFD tool, let's say, tool that allows to obtain these kind of outputs. So we model the two buildings and their context in MVMET. And for instance, we obtain maps like that. This is the building in London, and you can see the distribution of wind speed around the studied building, which is marked on the first map. According to different dominant direction of the wind. And you can see that the building, the shape of the building itself and the orientation with respect to the wind direction have a big impact on the wind speed on the facades. Even more clear is the impact of the built environment on the wind speed in the case of Cadiz. The building in Cadiz was located in a very narrow urban canyon, in a very dense urban texture, so the wind speed is definitely reduced compared to an open field or undisturbed field. To check what was the energy impact, or more than the energy impact, the impact of this wind speed reduction on the ventilation rates of the buildings, we use the MVMET outputs to force energy plus, basically. So we use the wind speeds calculated by MVMET, as input to the external nodes of the airflow network model, which is the model that is used in Energy Plus to calculate the ventilation rates in order to adjust the wind pressures at the different facades and obtain more, let's say, realistic ventilation rates. And the other effect that we checked using outputs from ENVIMAT was the impact of actual surface temperatures on the long wave radiation exchange of the building. So this was this has been done just for the building in Cadiz because it was really close to the facing building, and we wanted to check if we use the actual surface temperature of this facing building and the view factor of the studied building to the facing one, how much this could affect the heat loss through long wave radiation of the building. And we did so again using outputs of ENVIMAT and the object in Energy Plus that is called surrounding surface object that can be used for this purpose. And just to show some results for the building in Cadiz, in the first graph on the left, you can see that the wind speed on the facades of, for example, of two of the flats analyzed is much lower than the wind speed as calculated by Energy Plus, let's say, for the ventilation calculation. So it is important also to understand that when we run simulation in Energy Plus, not considering these actual wind speed values, we may have results that are not realistic. And now we will see how much is the difference. And also on the right side, you can see the difference between the surface temperature in red as calculated by ENVIMAT compared to the air temperature, which is the basic assumption made by Energy Plus also for surfaces. So in this graph, we represent the impact of using actual wind speed data instead of the standard data used by Energy Plus. The impact on the air change per hour of the different rooms of the building. So you can see that the, let's say, the blue bar represents the difference, and in some cases we have half of the air change per hour using actual wind speed, urban wind speed, compared to the undisturbed wind speed data. There are, of course, some rooms that are more affected than others. And this has an impact on the operative temperature. So in these graphs, you can see the difference in operative temperature determined by the decrease of the ventilation rates. That is on average below 1 degree, but with some maximum temperature difference up to almost 3 degrees. On the other hand, in this graph, we can see that the other effect, so the decrease of long wave radiation rate due to higher surface temperature in cities, has a lower impact. So the yellow bar represents the impact of using actual surface temperature in the prediction of the indoor operative temperature, compared to the gray bar that is when we neglect this effect. So in this case, the impact is no more than 0.3 degrees, so probably is not so important or less relevant, we can say, that urban wind data. Okay, so now I wanted to just show another study that is more focused on another time again generating future urban weather files, But in this case, we wanted to show, let's say, the different impact that the same building can have depending on a different location across the city. So this is another work that we developed for the RICOS project, and we presented at the Building Simulation Conference in 2021. So we developed this, we defined a methodology to include global and local climate modification in weather file, considering a building located in different locations across a city. Now, I will show why this is important. So we use London as a case study, and we choose 3 locations that were representative of London. So a suburban area, a low-density suburban area, a typical urban area of London with medium density and row houses, and the city center, which is much denser. So for these 3 areas, we developed an energy plus model, considering that the building in these 3 areas, of course, will be affected in different ways by the proximity to the other one, especially in terms of solar gains and in terms of heat island effect, because the heat island effect, the higher temperature increase in cities, will be more relevant in the denser city center than the suburban area. So in this case, we have developed a methodology that was similar to the previous one, but using other source data for the future climate. So we generated future typical meteorological years using more detailed high-resolution regional climate model data for the future prediction. So let's say that the future prediction are more detailed than the previous study. And similar to the previous one, we included the urban effects using the urban weather generator. And finally, we use this weather file to assess the overheating risk of the buildings in these 3 contexts, considering shading surfaces in Energy Plus to take into account of the different geometries of the urban context. And so, as I was saying, the future predictions are more detailed in this study, and in fact, we can see that in the future midterm, future long term, so 2015, 2090, and 90 in London, we have a significant increase of air temperature, but something that we could not see with methanol is that, at least according to some of the models, we can expect a reduction of the global horizontal radiation. So this also has have an impact on the building energy performance. Due to this, especially due to this reduction of solar radiation in the future, we do not expect an increase of the heat island effect. We actually can predict a slightly decrease of heat island effect in the future period, assuming that the city is not changing, of course. But of course, so the heat island effect is always adding to the climate change, air temperature increase, but we are not expecting an intensification of this phenomenon, we could say. And in this graph, sorry, I was showing also that the heat island effect with the red lines is higher in the city center compared to the typical urban area, while it is not present in the suburban area. And what I was mentioning before, if we consider the building in these 3 contexts, the proximity to other buildings and the density of the context in general may determine a decrease of the solar irradiation on the facade very significant. For instance, if we analyze the flat on the ground floor of the building in the city center, we can see that it has a reduction of the 60% of the solar irradiation on the facade compared to the suburban area without any kind of shading. So when we combine all these effects, and I'll go to the end of the presentation, what happens? If we analyze the ground floor, so the flat located in the ground floor, we can see that the flat located in the city center is the one that has a lower discomfort time. Let's say it has a decreased risk of overheating, thanks to the shadows of the surrounding buildings, basically. And so we have an increase of discomfort time with climate change, but basically the city location, the urban location, has a positive effect on overheating risk. On the other hand, when we analyze the middle floor, we see in change that the urban location has a worsening effect on the overheating risk of the building, and of course the percentage of time that the building is in a discomfort condition will increase much more than the ground location. And finally, if we analyze the top floor, of course, for its location, we know that it is one of the most affected by overheating risk. So the percentage of time that this flat is above the adaptive comfort temperature is higher and will significantly increase in the future period, much more than the other locations. And the urban context also has a detrimental impact due to the heat island effect and to the fact that we do not have the beneficial effect of shadows, basically. So, in conclusion, some conclusion of this presentation, we must be aware that the heat island effect in cities amplifies generally the negative effect of climate change on the annual energy load of buildings. So if we talk about energy loads in buildings, the heat island effect has a negative impact, which is on top of climate change. But also that in urban areas we have contrasting effects. So on the one hand, we have a decrease of wind speed that reduces the ventilation potential of buildings, but on the other hand, we have the positive effect of building shading on the cooling demand or thermal comfort in summer. So we always must consider all these effects in order to understand if the urban context is mitigating or amplifying the overheating risk associated with climate change. And therefore, we always should have, perform a multi-scale analysis to understand the relative impact of global, local, and macroclimate modifications on the buildings. And of course, the final impact will change also depending on the building itself, the fabric performance, the internal gain, and this is clear, but this research is wanted to show that also there are many other variables that are outside the building that affect its performance. And this is it for me. I hope it was interesting.
Thank you. Thank you very much, Agnese. It was very, very interesting, at least for me. I hope also for the others. If you agree, we keep some questions to the end of the presentation of Massimo also.
Yeah, sure.
Okay, thank you. Thank you very much.
Thank you.
So we can pass the role to Massimo.
I will do a presentation on the use of green infrastructure to mitigate the urban heat island phenomenon in Mediterranean climates. I think that most of people here knows that the urban heat island phenomenon depends on many factors, especially the macro and micro climatic context, as Agnese in her presentation showed very well. So we have to take into account the character of the urban fabrics, the geo and morphological conditions of the emplacement, and the climate. So a very good question can be which mitigation strategy can be the most effective for each macro and micro climatic context. And between between the various strategies to mitigate the urban heat island intensity, we can at least account the use of green infrastructure, both at the street level or incorporated in buildings envelopes, but also, for example, cool materials, urban ventilation, management of the air movement, and some other strategies like, for example, geothermal cooling, or the use of the water in urban blue spaces, or even with evaporative cooling effect directly at the street level or around the buildings. We should also consider changes, when permitted and possible, changes in the same urban fabrics, changes in heights of buildings, changes in urban density of sectors to be planned or to be renewed. At the same time, when we conduct an analysis of the theoretical analysis to select which intervention to be implemented, we can use different tools, and probably at a different scale of analysis for the planned intervention, we should use different tools more appropriated to the specific analysis we are running out. Typically, the urban heat island is a whole city phenomenon, more intense in the city center, as also Agnese showed very well. However, recent studies put in evidence that inside the city, there always are present some spots, some hot spots and some cold spots, and maybe in some cases, it's very interesting to focus on the urban heat island reduction in the hottest spots for the city. So in this presentation, I will show 3 cases of study. The first one in Barcelona, Spain. It is a very simple exercise using considering green roofs as mitigation strategy and using the tool INVEST. This is a GIS tool that can simply, but with many limitations, present an overview of the increase in the cooling capacity for the city with the application of the strategy. The second case is in Valparaiso, Chile, checking also with green roofs as a mitigation intervention, but this time using a very sophisticated tool like the ENVIMET to know the effect of the green roof implementation on the air temperature around the buildings. And the third case of study is a more complex study, considering 4 cities, 2 in Italy, Catania and Rome, and 2 in Chile, Valparaíso, Viña del Mar, and Santiago, using, in this case, the street trees as green infrastructure mitigation strategy, and urban weather generator plus transits as tools used for the analysis. All the cases of study are located in Mediterranean climate. So Mediterranean climates are climates belonging to the Copenhagen classification of temperated climates. Are located typically among latitudes 30 and 45 in both hemispheres. This includes the Pacific coast, both of North and South America, some small zones in South Africa and Australia, and of course all the Mediterranean basin. Of course, that microclimates are quite different among cities like this. From Los Angeles to San Francisco, the climate is changing in a quite consistent way, not to speak about changing from continent, etc. So the idea of Mediterranean climates includes very localized effects that are quite important on the specific intervention we can use. Moreover, there are differences in urban fabrics. Typically, American cities and also Australian cities are more dispersed and sprawled, while the Mediterranean basin typically presents a quite dense and compact city, of course, with differences from Algiers to Barcelona or Athens, but with higher densities than in the other continents. So the first case of study, a very, very simple exercise, we use the INVEST tool to check the benefits to implement green roofs on certain sectors of Barcelona city. And we selected the sector at the block level, at the building block level, by the density of people. So we selected the denser sectors with more than 0.5 people per square meter. This is about 20 square meter per people in residential buildings. So we selected Barceloneta, Barcelona Sands, and some parts of Horta and Guinardó as the building blocks to be restored and with the implementation of green roofs. In the software INVEST, we choose to change the 50% of roof surface to implement the green, and we changed the properties of albedo and evapotranspiration characteristics of the surfaces where we placed the intervention. We changed also the runoff retention to check if a mitigation strategy like this can be also a multi-risk reduction intervention. And INVEST calculates in a quite simplified manner a cooling capacity index defined as the local cooling potential respect to the maximum urbanization intensity of the whole city. And the results of the model are this one. We can visualize that the reduction coefficient for the urbanization intensity is changing in all the sectors considered by the analysis. And when we came to the numbers, we can see that we have about a 30% increase in the capacity to cool the city when the green roofs are placed. However, there are almost no global effect. The average urbanization intensity for the whole city remains the same. It's just a localized effect in the building blocks and surroundings where the green roofs are placed. If mitigation strategy is related to the exposition, to the number of people exposed to the urbanization, of course that the cooling capacity increased in the target points. This was the objective of this exercise, to know how much the cooling potential can be increased where is most needed. And finally, yes, this is a multi-risk mitigation strategy, because the runoff risk is reduced in about 30% in the target locations. Of course, that there are many limitations in using this tool. Invest is very simple, the calculation, only comparing the surface temperature of the satellite images, and no ventilation effect is considered, nor accurate radiation exchange among buildings and facades is accounted, and especially no three-dimensional assessment of urban temperature is done. It's just an analysis of the surfaces. So invest can be used when we have to check quickly and to recommend, for example, to urban planners some sectors to be prioritized in the selection for mitigation strategy, for mitigation interventions. The second case in Valparaiso, in this case, we first used a general urbanization intensity evaluation to select some neighbors where to model with EnviMet a complete analysis. And in this case, we checked also the strategy of green roofs, varying the percentage of roof surface occupied by green. So we compared the scenario to left green, the roofs without green, to use the 50% of the surface to place green, or to use the whole surface of roofs of the sector with green interventions. We changed the properties directly into the EnviMet model, and we ran out a set of simulation at different hours and different days of the typical year. And for example, we can see in the results for the summer solstice in the afternoon that there is a small effect of reduction in temperatures, about 0.5 degrees, not much than this, but we can see also how the effect of green roofs is changing the air temperature at different heights depending on the surface occupied by green. So we can use that strategy to mitigate also the urban heat island intensity at the street level. We can see also in this figure the effect of the breeze, that is a very important mitigation strategy for the cities on the Pacific coast, because we have a quite consistent and constant wind coming from the sea. And the idea is to use the combination of the air movement and the green on the roofs to try to mitigate also the street level. We are still researching on this. Depends on the type of green we can use on the roofs. And of course, that the effect can be increased by considering also interventions on building facades and on the street soils. In this case, EnviMet is a very complete tool with a calculation much more effective than other tools like the Invest. However, the problems are that is time consuming. We need important computational power to do the simulations, but we can obtain the vertical profiles for high temperature, allowing more informed and precise decisions to be taken. The third case I will present is a study on green infrastructure on the street level. To plant trees on the street to shadow facades and roofs of buildings, and we compare different cities in the Mediterranean emplacement. We select some neighbors in Viña del Mar, in Santiago de Chile, and in 3 locations in Italy, in Catania, and in 2 urban peripheries of Rome, Casale Caletto and Tor Bella Monaca. We consider in this case the local availability of space to plant the trees. This is quite important because in general there are many studies considering an isolated buildings flying without the urban context, and they're placing trees to check the effect of shadows and maybe other effects, evapotranspiration and wind modifications, but just very theoretically to putting the trees all around the building without considering a real context. So in this case, there was a study that we did with researchers for urban planning departments in Catania and in Rome and here in Chile. We decided to consider real conditions. So the green intervention was done where there is the possibility to do it. And this is changing, of course, in one case and another. So each configuration was conformed by a building with an existing building with some characteristics, form, materials, etc., and the availability of space where to put the trees. so the distance from the facade, for example, are changing from Catania to Rome in each case. The properties of trees was modeled using the geometry of an adult tree of different species, and the radiation properties were modeled using the gap light analyzer tool. Then the urban heat island for each microclimatic location was assessed with the urban weather generator, and the buildings was modeled in transits, and then we ran the simulations considering the presence of the trees or not. And we estimated the reduction in cooling on in cooling loads of simulated buildings. Buildings were grouped in categories, basically just with very similar to the Tabula project building categories. And we divided in 4 basically size and form of the plant floor. So we decided to group the buildings in C shaped buildings, T shaped buildings, L and I shaped buildings. Materials properties was used was the same for all the cases. This is a little approximation because materials used in Chile are sometimes different from building materials used in Italy, but we selected to not to change the values, to not introduce some noise in the simulation results. We also used the same operation settings for all the cases, light gains, cooling set points, and occupancy of people in the management of the solar shading by the same people simulated as an ideal user that is opening and closing blinds depending on the penetration of the solar radiation. The building shape determine the window to wall ratio, and there are some shapes with more exposed windows to the sun than others. The trees are modeled with the shadow angles that permits the radiation on the building facades, and in some cases, in the Pinus case, basically as on the roof. And we modeled the solar permeability with the gap light analyzer for 3 types of trees, 3 species: the Pinus, Platanus orientalis, and the Ficus benjamina. This was the 3 species we modeled. Coming to the results, we see that the cooling loads reductions using the green infrastructure on all the available space around the buildings for these 120 configurations we analyzed are in a quite variable range, from 5% to almost 50% of cooling needs reduction. The reduction in cooling needs is higher in percentage when the initial, the base case need was lower. This is quite typical when you have lower needs, the intervention is in percentage more effective. But there are many cases with important reduction of 30–40% in cooling loads, especially using the pines, the species that with the umbrella effect is more effective to shower, especially the last floor and the roof of the building. Now, one of the big problem is how to decide where to put the trees and when it is really convenient to do that. But to do this, we need maybe to consider more factors and not only the energy consumption or the comfort that we can obtain both outdoor and indoor. So I think that as a conclusion and establishment of future works and maybe important decision to take now, we can see that we can say that green infrastructure interventions are always very important to reduce the local urbanized intensity, not only in Mediterranean climates, but especially in Mediterranean climates. Benefits should be accounted at different scales using the tool more effective for the scale of analysis. So maybe invest, very useful to communicate the general improvements to stakeholders. MVMET is needed to specifically test the influence of some specific intervention at the building surrounding levels, and urban weather generator is maybe the most useful tool to be used in combination with building performance simulation tools. But we have the open questions and the other parameters we have to add to our studies. For example, other factors affect a global evaluation of the mitigation strategy. When we use green infrastructure, especially, we have the use of water for irrigation to be accounted. And in the case of trees, maybe we need more water for irrigation than in the case of green roofs or green facade, where we can use more controlled irrigation systems. Very important is the capacity of stakeholders to take a decision quickly. You imagine if you are working as urban planner at the municipality and you have to decide which part of the street should be dedicated to trees, you have to select the species, look to the distance from the facades of buildings, and also to stay with another boundary condition, for example, the continuity of the green infrastructure to be used by people to move or for bicycles, etc. We should also consider the capacity of computational processes to help the decisions of stakeholders. We need also to put all together. We can have different scale analyzed with different tools, and we need to decide with all this information really what which mitigation strategy can we put in the reality. And we have to focus on multi-risk reduction if possible. Just as a little idea for future studies, we are developing a machine learning study to help urban planners to take decisions. So, for example, we can run a certain number of simulation of these configurations, considering buildings and surroundings with or without green infrastructure interventions, and then we can check if the machine is able to do an estimation of the final energy convenience to have the green infrastructure based on the learning process on the previously run simulations. So is the machine able to generalize our study? And we checked for the 120 simulations we did in Mediterranean climates, asking to the machine to classify in a supervised manner if the cooling loads are reduced by the green infrastructure in less than 5%, between 5 and 50, between 50 and 25, between 25 and 35, or more than 35. It was maybe the target objective to reduce more than in a 35% the cooling load. And we see that the mix of different algorithms, especially we used random forest, LOS, KNN neighbors, and GLM. And with the mix of all these, with the ensemble of the algorithms, we obtained a quite good result, and we have a positive recognition of the machine of 75% of the cases, correctly assigned in the 5th categories classification strategy. When we used only 2 categories, more or less than 50% of cooling load reduction, the accuracy of the machine learning is of 95%. So it's really very accurate to determine if the energy load will be reduced in more than 50% or not. And this is a very good information for stakeholders that have to decide if to put trees in this street, shadowing this facade of buildings or not. Of course, that the arbitrary value of 50% can be changed. We can use 20 or another value. Of course, that we focused until now only on Mediterranean climates. We should check this kind of computational learning strategies on more situation, considering the climate variability that maybe can reduce the accuracy of the predictions. But is one of the open questions for research, and I think that you can be interested in. And finally, some references on the previously published work on these topics, quite recently, between 2020 and 2022. And thank you very much.
Thank you, Massimo. Okay. I collected a couple of questions for the relator, since we are recording that could be listened in any case. The first one is for Professor Salvati. We have seen very interesting the interest in making morphing climate using the Copernicus, or in any case connected future weather databases. We are also working in that topic, also inside the PRELUDE project. And so I collected for one of the research staff here in Polito, and also for one of our technical partner in the projects, a question about the things. Now, we are now integrating in our tool an automatic, you can say, generator of typical weather file for the ERA5 database for running energy plus and sensitivity analysis. But for future weather, that's less easy in one way to identify in codecs or in regional models in general, you can say, available data in the sense of the
early dimension, no? Because generally a tree early or daily or this type of distribution of the peak. And in addition to that, in some way, it's also difficult to find model that has, we can say, inside all the needed variable to feed an energy plus simulation, no? Or to derive from the energy plus simulation. So one of the questions is that, how do you face this type of issue in some way? So you do consider, for example, one single model or multiple model aggregated?
In the experience I have so far, which is not so extended, we chose the model that was like that performed better compared to the historical observations. So since we have regional climate predictions that were run for an historical period, we could compare, let's say, the performance of the model compared to the actual weather. And we chose for the study that I presented the model that was predicting, let's say, was more close to the actual weather that happened. But the best way would be to use to use more models and then perform a sensitivity analysis or perform simulation using more prediction. Actually, it is true. So the Cordex database is a very useful database for this. There are results for different models. And that will be, I think, the best way to proceed. Of course, it's quite a long task to perform because there are many variables. And in fact, for instance, we can say that the models are quite in agreement for what concern the air temperature predictions, more or less, but there are models that predict a decrease of solar irradiation in the future and others that do not predict this. So this is also a big question. We can expect a reduction of solar irradiation due to the increase of particles in the atmosphere. So it's possible, but of course it is not determined. So the safer thing would be to use a range of models.
Yeah, that's totally true. Thank you.
Thank you.
Thank you very much. Okay, Massimo, on your point of view, that's a general question. Potentially, it's not the best one, but it's giving, I think, an excellent topic. When you consider the vegetation, which is always a very important mitigation action in the city level point of view also, but it's not so easy to define in one way because trees are growing, no? At least at the beginning. How do you think is faced this type of problem? So, for example, if you are asked to manage with this type of tool a design of part of the city, not to counterbalance some overheating or some climate change aspect, and you decide to, like it is in some of the recovery plan or this type of application at European level, to plant new trees, how do you think is faced at this part in the design? We proceed with a sort of progressive check with small tree, medium, and fully developed tree, or we generally consider for the design the fully developed or the existing trees, and for the new one, what we do?
Yes, thank you for this question. Very, very, very interesting. I think that in practice, the analysis at the energy level are typically done considering the complete developed trees, so the adult trees, just like we did in our simulations. But placing the real problem in the urban planning, the decision-making process,
they also include more factors. For example, they consider the growing time for the trees and try to select trees that are faster development, no, to conduct to the desired situation faster. Of course, that the mitigation of the urban climate changes should also, in my opinion, consider long-term effects. So the idea can be to place better trees in the long-term prevision, and then like you said, you can monitoring or control the benefits year by year until the final condition is reached.
Thank you. That's always in some way important, interesting topics. This one, especially for architects or designer, because they at the end potentially will use, especially the students in future, some of these application, and this tool eventually they don't use potentially the one present in the class in its course, but they always have the interesting to potentially use it in future. At least one of them. So I really thank you to both. Thanks Agnese, thanks Massimo, very a lot for this interesting presentation, and see you soon, as we can say, and thank you again.